Hello there, and welcome back to the Sleepy Science Society. Tonight, we're drifting into a world where the sky was not merely something to observe, but a sacred text written in light and shadow, a celestial tapestry that held the secrets to time itself, to the rhythms of planting and harvest, to the movements of gods, and to the very fabric of existence. We're traveling back through the centuries to explore the remarkable astronomical achievements of the ancient Maya, a civilization that reached heights of celestial understanding that would not be matched in Europe for centuries to come. As you settle into your comfortable space, allowing your breathing to slow and your body to relax, I invite you to imagine standing in a plaza beneath a tropical night sky so clear and dark that the Milky Way blazes overhead like a river of stars. Around you rise stepped pyramids, their stones still warm from the day's sun, and somewhere above, in a circular tower unlike any other structure in the city, a priest astronomer watches Venus emerge on the western horizon, carefully marking its position against the backdrop of constellations, adding one more observation to centuries of accumulated knowledge. If you enjoy these quiet explorations through the wonders of science and history, I invite you to like this video and subscribe to our channel. It helps others find their way to this peaceful corner of learning, one sleepy mind at a time. But for now, there's nothing you need to do except rest, breathe, and let your imagination drift back through time to witness one of humanity's most beautiful unions of science, mathematics, and spirituality. Let's begin our gentle journey into the starlit world of Mayan astronomy, the sacred sky, where Earth met heaven. To understand Mayan astronomy, we must first understand that for the ancient Maya, there was no separation between science and spirituality, no boundary between the practical and the sacred. When a Mayan astronomer climbed the steep steps of an observatory to watch the sky, they were not simply recording data. They were reading the intentions of gods, deciphering messages written in the movements of celestial bodies, interpreting the cosmic order that governed everything from the timing of royal ceremonies to the planting of maize in distant fields. The Maya lived across a vast region of Mesoamerica, from the highlands of what is now Guatemala through the lowland rainforests of the Yucatan Peninsula in Mexico, and into parts of Belize, Honduras, and El Salvador. This civilization flourished for thousands of years, with its classic period spanning from around 300 to 900 years after the Common Era, though Mayan astronomy had roots reaching back much earlier and continued evolving long after. Unlike the relatively clear horizons of Mesopotamia or Egypt, where other ancient astronomers plied their trade, the Maya worked in regions where dense jungle often obscured the horizon. This geographical reality shaped their astronomical practices in fascinating ways. They became particularly skilled at zenith observations, noting when the sun passed directly overhead, an event that never occurs outside the tropics. They built tall structures that allowed them to see above the forest canopy, creating unobstructed views of the heavens from platforms and towers that rose like stone-true trees above the leafy sea below. The night sky was, to the Maya, a living realm populated by deities whose movements told stories and determined fates. The path that the sun, moon, and planets traced across the sky, what we call the ecliptic, was understood as a great celestial road traveled by divine beings. Every celestial body had personality, intention, and influence. The sun was not merely a ball of burning gas, but a deity whose daily journey from east to west represented life, death, and rebirth. The moon cycled through phases that echoed in themes of growth, fullness, decline, and renewal. And Venus, Venus was perhaps most significant of all, a warrior deity associated with warfare, political power, and dramatic transformation. This worldview meant that astronomical observations carried enormous weight in Mayan society. The ability to predict when Venus would appear as the morning star, when eclipses would darken the sun, or when the seasons would shift gave priest astronomers tremendous authority. Kings and nobles consulted these scholars before making major decisions, timing battles and coronations to align with favorable celestial configurations. To know the sky was to possess a form of power, a capacity to anticipate the movements of divine forces and to synchronize human activity with cosmic rhythms. Yet this spiritual dimension did not make Mayan astronomy any less rigorous or scientific in its methodology. The Maya were extraordinarily patient observers who recorded celestial phenomena with remarkable precision across generations. They developed mathematical systems capable of tracking and predicting astronomical cycles with an accuracy that would astound later scholars. They understood that the patterns they observed were not random, but followed rules that could be learned, recorded, and used to project far into the future. Imagine a young apprentice astronomer in the year 800, learning from a master who had spent decades watching the sky. The knowledge being transmitted was not the work of one lifetime, but the accumulated wisdom of countless observers stretching back through the centuries. Each generation refined the calculations, corrected small errors, and added new layers of understanding. This was science in its purest form, the patient building of knowledge through observation, record-keeping, and the willingness to test predictions against reality. The Maya understood that time was cyclical, that patterns repeated, and that by understanding these cycles, one could glimpse both past and future. This cyclical view of time was fundamentally different from the linear conception that would later dominate Western thought, and it shaped how the Maya approached astronomy. They were not trying to understand the physical mechanisms behind celestial movements, as Greek philosophers would later attempt. Instead, they focused on the patterns themselves, on the what and when rather than the why, and in doing so achieved predictive capabilities of extraordinary sophistication. The calendars, measuring the infinite dance. At the heart of Mayan astronomical achievement lay their calendar systems, interlocking cycles of remarkable complexity that wove together cosmic time, sacred ritual, and practical necessity. The Maya did not have just one calendar. They had multiple calendrical systems, each serving different purposes, and the genius lay in how these systems meshed together to create a comprehensive timekeeping framework unlike anything else in the ancient world. The most sacred of these was the Tzolk'in, a ritual calendar of 260 days. This calendar combined 20 named days with 13 numbers in a continuous cycle. The day names included creatures and forces both earthly and mystical. Imix, Ike, Akbal, Ka'an, Chikchan, Kimi, Manik, Lamat, Muluk, Oke, Chuen, Ib, Bn, Ix, Men, Keib, Kabean, Etsanab, Gawak, and Ajah. Each name carried its own significance, its own energy and association. The numbers 1 through 13 combined with these 20 names, creating a system where each day had a unique designation within the 260-day cycle. Once that cycle completed, it began again, an eternal wheel turning through the centuries. Why 260 days? The truth is, we don't know with absolute certainty, though scholars have proposed numerous theories. Some suggest it relates to the human gestation period, approximately 266 days from conception to birth. Others point to agricultural cycles or mathematical properties that emerge when combining factors of 13 and 20. Some researchers have noted connections to Venus cycles, as 5 Tzolk'in cycles equal 8 Venus years with remarkable precision. What we do know is that the Tzolk'in was considered profoundly sacred. It was used for divination, for determining auspicious days for ceremonies, marriages, warfare, and planting. Daykeepers, specialists who maintained this calendar's wisdom, would consult it to understand the character and fortune associated with any given day. Even today, among Maya descendants in Guatemala and southern Mexico, daykeepers continue to track the Tzolk'in, maintaining an unbroken thread of practice stretching back over 2,000 years. Running parallel to the sacred Tzolk'in was the Haab, the solar calendar that tracked the agricultural year. The Haab consisted of 18 months, each containing 20 days, plus a short period of 5 days considered unlucky and dangerous, called the Waib. This gave a total of 365 days, closely approximating the actual solar year of approximately 365 and a quarter days. The 18 months of the Haab had names reflecting the agricultural and seasonal cycles important to Maya life: Pop, Wo, Sip, Sots, Sek, Shul, Yaxkin, Mol, Chen, Yax, Sak, Ke, Mak, Kaankin, Muwan, Pax, Kayab, and Kumku, followed by the 5-day Wayeb. Each month was associated with particular ceremonies and activities. The Haab allowed farmers to time planting and harvesting, priests to schedule major religious festivals, and society to maintain its agricultural rhythm. Now, here is where things become beautifully intricate. The Tzolk'in and the Haab ran simultaneously, like 2 gears of different sizes turning together. Any given day had both a Tzolk'in date and a Haab date. Because 260 and 365 share only a few common factors, it took exactly 18,980 days, or approximately 52 solar years, for the 2 calendars to return to the same combined position. This 52-year cycle, called the calendar round, was tremendously important in Mayan culture. The completion of a calendar round was a major occasion for celebration and ritual renewal. But the Maya were not satisfied with tracking only 52 years at a time. They needed a system that could record dates across vast spans of history, that could look backward to mythological creation and forward to distant futures. For this, they developed the long count calendar, perhaps their most remarkable chronological achievement. The long count measured time from a zero date, a mythological starting point that in our calendar system corresponds to August 11th, 3,114 years before the Common Era, though we should note this is a correlation that scholars have debated. From this starting point, the Maya counted days forward using a vigesimal, or base 20, system with one crucial modification. The smallest unit was the kin, a single day. 20 kin made a winal, approximately 1 month. 18 winal, not 20, made a tun of 360 days, roughly 1 solar year. Here, the Maya departed from pure base 20 to keep the tun close to the actual solar year. 20 tun made a ka'atun of 7,200 days, approximately 19 and a half years. Finally, 20 ka'atun made a ba'aktun of 144,000 days, approximately 394 years. Long count dates were written as 5 numbers, representing ba'aktun, ka'atun, tun, winal, and koan. So a date might be written as 9.5 and 5.18, indicating 9 ba'aktun, 12 ka'atun, 11 tun, 5 winal, and 18 kin had elapsed since the starting point. This system allowed the Maya to record dates with absolute precision across thousands of years. Stone monuments, or stelae, throughout the Maya world bear long count dates commemorating royal accessions, military victories, and important ritual events. The precision and scope of these calendar systems reveal minds deeply engaged with time's passage, with cycles within cycles, with the ways that moments echo across years and centuries. The Maya did not see time as a simple linear progression from past to future, but as a complex spiral where similar patterns recurred, where understanding the cycles of the past illuminated the patterns of the future. And here's what makes this even more remarkable. The Haab calendar, with its 365 days, was extraordinarily accurate. The Maya knew the solar year was not exactly 365 days, but approximately 365.2422 days. They didn't incorporate leap years in the way the later Gregorian calendar would, but they understood the discrepancy and tracked it over long periods. Some evidence suggests they made corrections over very long cycles to account for this drift, demonstrating their awareness that even their sophisticated calendar needed occasional adjustment to maintain alignment with astronomical reality. The development of these interlocking systems required not just astronomical observation, but also advanced mathematics. The Maya had developed a true understanding of zero as a number and placeholder, a concept that European mathematics would not fully embrace for centuries to come. Their vigesimal number system used dots for ones, bars for fives, and a shell glyph for zero, allowing them to write very large numbers and perform complex calculations necessary for their astronomical predictions. When night fell, and the priest astronomers climbed to their observation posts, they carried with them these sophisticated tools for measuring time. They could situate any observation within multiple temporal frameworks simultaneously, understanding how the moment fit into the sacred Tzolk'in cycle, the solar Haab year, and the vast sweep of the long count. This multi-layered temporal awareness was the foundation upon which all their other astronomical achievements rested. Venus, the fearsome warrior star. Among all the celestial bodies tracked by Mayan astronomers, Venus held a place of special fascination and dread. This brilliant planet, the second brightest object in the night sky after the moon, was associated with warfare, sacrifice, and dramatic change. The Maya called Venus by names including Tzolk'in, meaning great star, and understood it to be a deity of tremendous power and unpredictable temperament. What made Venus particularly interesting to Mayan observers was its complex dance across the sky. Unlike the outer planets, which appear to move steadily westward relative to the stars with occasional retrograde periods, Venus displays a striking pattern of appearances and disappearances. For approximately 263 days, it appears as the morning star, rising in the east before dawn with a brilliance that can actually cast shadows. Then it disappears from the morning sky, remaining invisible for about 50 days as it passes between Earth and the Sun. Next, it emerges in the western sky as the evening star, visible after sunset for approximately 263 days. Finally, it disappears again for about 8 days as it passes on the far side of the Sun, before the entire cycle repeats. This complete cycle, called the synodic period of Venus, takes approximately 584 days. The Maya tracked this cycle with extraordinary precision, calculating it to be 583.92 days, a figure that modern astronomy confirms as remarkably accurate. This precision was achieved through centuries of patient observation, with each appearance and disappearance carefully recorded, creating a database of Venus sightings spanning generations. The Dresden Codex, one of only 4 Maya books to survive the Spanish conquest, contains the most detailed record of Mayan Venus observations that has come down to us. This accordion-folded book, made from bark paper and covered in intricate hieroglyphs and illustrations, ended up somehow in Dresden, Germany, where it was recognized in the 1800s as an astronomical almanac of extraordinary sophistication. The Venus table occupies several pages of the Dresden Codex and represents what may be the work of a specific astronomer working in the city of Chichen Itza during the Terminal Classic period, around 900 years after the Common Era. Recent research by scholars like Gerardo Aldana suggests we can actually narrow down when this individual made a crucial mathematical discovery about correcting the Venus calendar. This wasn't just numerology or abstract mysticism. This was an actual scientific breakthrough, the result of one person carefully observing, calculating, and realizing how to account for the small discrepancies that accumulated over multiple Venus cycles. Here's what made the Venus problem so challenging. While the average synodic period is 584 days, the actual period varies slightly due to the elliptical nature of both Earth's and Venus's orbits. Over multiple cycles, these small variations add up. The Dresden Codex contains correction factors, adjustments that needed to be applied periodically to keep the Venus predictions aligned with actual observations. Working out these correction factors required sophisticated mathematics and the accumulated data of many, many Venus cycles. The Maya noticed something else remarkable about Venus. 5 Venus cycles equal approximately 8 solar years. 5 times 584 days equals 2,920 days. 8 solar years equals approximately 2,922 days. The match is not perfect, but it's close enough that the Maya could use this relationship as another layer in their calendrical system. This 8-year cycle, called the Venus round, meant that Venus would return to approximately the same position relative to both the Sun and the Tzolk'in calendar, creating another wheel within wheels. The Venus table in the Dresden Codex is laid out in a grid showing the positions of Venus on specific dates in the sacred Tzolk'in calendar. By consulting this table, a priest could determine when Venus would next appear as morning star or evening star, information used to time important events. There is strong evidence that the Maya coordinated military campaigns with Venus appearances, particularly the heliacal rising of Venus as morning star, which was considered an especially potent and dangerous time. Archaeological evidence supports the importance of Venus in Mayan thought and practice. At Chichen Itza, the structure known as El Caracol, which we'll explore in more detail shortly, has windows specifically aligned to the northernmost and southernmost points where Venus sets on the horizon. These extreme positions occur at 8-year intervals, reflecting that 8-year Venus cycle the Maya had identified. The fact that architectural features were permanently built to align with Venus positions demonstrates how central this planet was to Mayan astronomical and religious practice. At other sites, like Uxmal, the governor's palace has a doorway aligned with Venus's southernmost setting position. At Copan, in what is now Honduras, hieroglyphic texts record Venus events, demonstrating that Venus observations were being made and recorded at least 200 years before the Dresden Codex was created. The Maya were maintaining astronomical records across centuries, with later astronomers building on the work of earlier ones, refining and correcting their predecessors' calculations. The iconography associated with Venus is fascinating and sometimes disturbing. Venus was often represented as a warrior deity, sometimes shown with a spear or atlatio, weapons used in warfare. The feathered serpent deity Kukulkan, who became increasingly prominent in later Maya culture, had strong associations with Venus. During periods when Venus was invisible, transitioning between morning and evening appearances, the Maya believed the planet was traveling through the underworld, and these were considered particularly dangerous times. It's worth pausing to appreciate just how remarkable these Venus observations were. The Maya achieved this precision without telescopes, without modern timekeeping devices, without even metal tools for construction or writing implements beyond stone, wood, bone, and shell. They used naked eye observations, patience, and brilliant mathematical minds. An astronomer would climb to an observation point, note Venus's position against background stars or landscape features, and record this in their system of glyphs. Over decades and centuries, these observations accumulated into a body of knowledge that allowed accurate predictions. The lunar month, as calculated by the Maya, was 29.5308 days. Modern astronomy places it at 29.53059 days. The difference is incredibly small, less than half a second per day. Achieving this accuracy required tracking the moon's phases over many, many cycles, noting when it returned to the same phase at the same time, and using this data to calculate an average that accounted for the irregularities in the Moon's actual orbit. The Sun and Moon, marking time and predicting darkness. While Venus may have been the most dramatic celestial body in Mayan astronomy, the Sun and Moon were perhaps the most fundamental. The Sun's movement defined the agricultural year, marked the seasons, and provided the framework for the solar Haab calendar. The Moon's phases governed ritual timing and provided the Maya with another powerful tool for tracking time and predicting celestial events, particularly the awe-inspiring phenomenon of eclipses. The Maya were intimately familiar with the Sun's annual journey across the sky. Living in the tropics, they experienced the Sun passing directly overhead, an event called the zenith passage that occurred twice each year at their latitude. This was a phenomenon that simply doesn't happen in places like Europe or most of North America, where the Sun never reaches the zenith. For the Maya, these zenith passages were significant markers in the calendar, carefully noted and often commemorated in architecture. At the site of Edzana in the Yucatan Peninsula, a large mask of the sun god positioned atop a platform aligns perfectly with the Sun's zenith passage. Near the latitude of this observatory, which was a major city of some 20,000 people in the early centuries after the Common Era, the Sun passes through the zenith at noon on July 26th. Remarkably, the Maya chose this date as their new year in at least some calendrical reckonings, a choice that reflected their careful observation of this uniquely tropical phenomenon. The Maya also tracked the solstices and equinoxes, the 4 key points in the solar year. The summer solstice, around June 21st, is when the Sun reaches its northernmost point in the sky, and the day is longest. The winter solstice, around December 21st, is when the Sun reaches its southernmost point and the day is shortest. The equinoxes, around March 21st and September 22nd, are when day and night are approximately equal in length, and the Sun rises due east and sets due west. Many Mayan structures incorporate solar alignments that mark these important dates. At Uaxactun, the Group E complex served as a solar observatory, with sight lines from a central point to structures on the eastern horizon that allowed precise determination of solstice and equinox dates. An observer standing at the right location would see the Sun rise over one building on the summer solstice, over another on the equinoxes, and over a third on the winter solstice. This created a giant 3-dimensional calendar marked in stone and aligned with cosmic precision. Perhaps nowhere is Mayan solar awareness more dramatically demonstrated than at Chichen Itza's El Castillo Pyramid, also called the Temple of Kukulkan. This magnificent stepped pyramid has exactly 91 steps on each of its 4 sides. 91 steps times 4 sides equals 364 steps. And if you add the temple platform on top as the final step, you get 365, the number of days in the solar year. The pyramid itself is thus a stone calendar, but El Castillo's solar connections go deeper. During the spring and autumn equinoxes, as the afternoon sun strikes the pyramid at just the right angle, a shadow pattern forms on the northern staircase. Triangles of light and shadow link up along the side of the stairs, connecting to the massive serpent head sculptures at the base. The effect creates the illusion of a giant feathered serpent. likely representing Kukulkan, descending the pyramid. This phenomenon lasts for a few hours and draws thousands of visitors today. But imagine witnessing it 1,000 years ago, seeing your deity physically manifest in light and shadow as a direct result of the sun's position, confirming the order of the cosmos and the power of the priest astronomers who designed this marvel. The moon presented its own set of challenges and opportunities. The lunar month, the time from new moon to new moon, is approximately 29.5 days, but the exact period varies slightly due to the moon's elliptical orbit and other factors. The Maya tracked lunar cycles with the same meticulousness they brought to solar and Venus observations. Stone monuments often included supplementary series of glyphs providing detailed lunar information, including how many days had elapsed in the current lunation, the length of that particular lunation, and which number the lunation was in a series. Why such detailed lunar records? One reason was eclipse prediction. Eclipses, both solar and lunar, were considered extremely significant and potentially dangerous events by the Maya. A solar eclipse, when the moon passes directly between Earth and the sun, casting its shadow on our planet and temporarily blocking the sun's light, must have been terrifying to witness if unexpected. A lunar eclipse, when Earth's shadow falls on the moon, turning it a deep red color, was equally portentous. The Maya discovered something that allowed them to predict eclipses with reasonable accuracy. Eclipses follow patterns. Because of the geometry of Earth's orbit around the sun and the moon's orbit around Earth, eclipses can only occur when the sun, Earth, and moon align in specific ways, and these alignments repeat in cycles. The most important of these cycles is the Saros cycle, approximately 6,585 days, or roughly 18 years and 11 days. After one Saros cycle, the geometry of Sun, Earth, and Moon returns to a very similar configuration, meaning eclipses often repeat with Saros periodicity. The Dresden Codex contains eclipse tables showing a sophisticated understanding of these patterns. Pages of the Codex display eclipse glyphs spaced at correct eclipse intervals. By consulting these tables and knowing where they were in the cycle, Maya astronomers could predict when eclipses were possible, though not every eclipse visible somewhere on Earth would be visible from a particular Maya city. So, some predictions wouldn't be confirmed locally. The ability to predict eclipses conferred tremendous authority. Imagine being able to announce, weeks or months in advance, that on a specific day the sun would be devoured by darkness, and then having it actually happen exactly as you predicted. This was power of an almost godlike nature, demonstrating that the priest astronomers could foresee the actions of the heavens, that they possessed knowledge ordinary people did not and could not access. There is also evidence of an 819-day count in some Mayan inscriptions, which some researchers believe may be related to tracking the orbital cycles of Jupiter, though this remains less certain than the Venus, solar, and lunar observations. What's clear is that the Maya were systematically tracking multiple celestial bodies, recording their movements, and using this information to maintain their complex calendrical systems and make predictions that proved accurate time and again. The observatories. Architecture aligned with the cosmos. The Maya encoded their astronomical knowledge not just in books and carved inscriptions, but in the very stones of their cities. Throughout the Maya world, structures great and small incorporated alignments to celestial phenomena, creating an architecture where buildings functioned as instruments for marking time and observing the heavens. Among these, certain structures stand out as clear examples of dedicated astronomical observatories, places specifically designed for systematic sky watching. The most famous of these is undoubtedly El Caracol at Chichen Itza, a building so unusual in Mayan architecture that its purpose has been evident to researchers since serious archaeological work began. El Caracol, Spanish for the snail, gets its name from the spiral staircase hidden inside its cylindrical tower. Rising from the flat landscape of the Yucatan Peninsula, where dense jungle once obscured horizons, this multi-level structure provided Maya astronomers with an elevated vantage point for unobstructed views of the sky. El Caracol sits atop a large rectangular platform, itself elevated above a lower platform. This stacking gives the observatory considerable height, allowing observers to see above the forest canopy. The building was constructed around 906 years after the Common Era during the post-classic period, though there is evidence of earlier structures beneath, and astronomical observations at the site extend back further in time. The architecture of El Caracol is remarkably sophisticated. The building consists of 3 superimposed structures. The first level is formed by 2 concentric circular walls, creating a corridors between them. The outer cylinder has 4 doorways positioned at the cardinal directions: north, south, east, and west. Inside, another cylinder with 4 doors arranged in a quinconx pattern, offset from the outer doors, creates a maze-like interior that controls light and provides multiple sight lines. At the center rises a solid core of masonry containing that narrow spiral staircase that gives the building its name. This stairway leads up to the upper chamber, which once had a domed roof, now collapsed. In the walls of this upper chamber were small windows or viewing ports, carefully positioned openings that functioned as targeting devices for astronomical observations. Today, only 3 of these viewing ports survive well enough for researchers to determine their alignments, but these 3 tell a remarkable story. One port aligns with the setting point of the sun at the spring equinox on March 21st. Another aligns with the setting point of the sun at the summer solstice on June 21st. Most intriguingly, one of the diagonals created by looking through multiple structural features points to the northernmost setting position of Venus, an extreme reached once every 8 years as Venus oscillates between northern and southern limits, like the sun does with its annual cycle, but on a much longer timescale. A separate sight line points to the southernmost setting position of Venus, again marking the extreme of Venus's 8-year cycle. The care taken to align these permanent stone structures with Venus positions demonstrates just how important Venus observations were to the Maya at Chichen Itza. The astronomer working in this building would have watched Venus sink toward the horizon through these viewing ports, noting when it reached its extreme positions, confirming and refining the calculations recorded in texts like the Dresden Codex. Researchers who have studied El Caracol's alignments have identified sight lines to approximately 20 out of 29 possible astronomical events of interest, including various solstice and equinox positions, Venus extremes, and likely positions of certain bright stars. This structure was not just a symbolic representation of cosmic order. It was a functional scientific instrument, a place where systematic observations were made and recorded. The elevated position of El Caracol served another purpose beyond seeing above the jungle canopy. In the Yucatan's flat terrain, there are few natural elevated points. By building upward, the Maya created artificial high ground from which the circular horizon was equally accessible in all directions. An observer could move around the upper chamber, tracking celestial bodies across the entire sky, watching the stars wheel overhead, noting where planets rose and set, measuring the moon's changing positions through its monthly cycle. But El Caracol was not the only observatory in the Maya world. At the site of Uaxacten in Guatemala, the Group E complex represents an even earlier form of solar observatory. Dating to the late Preclassic period, possibly as early as 200 years before the Common Era, this complex consists of a western pyramid from which observations were made, and 3 structures on the eastern horizon. Sightlines from the pyramid to these eastern structures align with sunrise positions on the summer solstice, the equinoxes, and the winter solstice. This created a horizon calendar where the sun's annual motion could be tracked by noting which structure it rose behind on any given day. This Group E pattern, named after the first one identified at Uaxactun, has since been recognized at numerous other Maya sites, suggesting it represented a standardized form of solar observatory, a template that Maya builders replicated across their civilization. The consistency of this pattern indicates shared astronomical knowledge and practices across the far-flung Maya world. At Edzna, another Yucatan site, a cleverly designed stone pedestal in the courtyard in front of the main 5-story pyramid allowed priests to measure the sun's zenith passage. At the moment when the sun stood directly overhead, the pedestal would cast no shadow, or only a shadow directly beneath itself, marking this crucial date in the tropical calendar. The main pyramid itself, like many Maya structures, incorporated astronomical alignments in its orientation and construction. Uxmal, in the Pius region of Yucatan, contains several structures with astronomical significance. The governor's palace has a doorway that aligns with Venus's southernmost setting position, creating a sightline that connects the building to this important celestial marker. The precision required to achieve this alignment during construction demonstrates the priority given to astronomical considerations in Mayan architecture. Even structures that weren't primarily observatories often incorporated cosmic symbolism. The stepped pyramids that dominate Maya cities represented sacred mountains connecting earth and sky. Their stairways, ascending from ground level to elevated temples, symbolize the path between worldly and celestial realms. Many pyramids have 9 levels, representing the 9 levels of the underworld in Maya cosmology. The temples at their summits, where rituals were performed, placed priests and nobles closer to the heavens, in liminal spaces between human and divine domains. The planning required to create these alignments was considerable. Before construction began, astronomers and architects had to determine the precise orientations needed. This required years of observations to establish accurate solar and Venus positions. They had to account for the local horizon's features, calculate sightlines, and then convey this information to builders who would set foundation stones with the necessary precision. The fact that many of these alignments remain accurate today, 1,000 years later, speaks to the skill of Maya architects and the importance of getting the astronomy right. In modern times, archaeologists use sophisticated surveying equipment to measure building alignments. They compare these measurements to astronomical calculations to determine what celestial events the structures marked. In many cases, the correlations are so precise, within small fractions of a degree, that coincidence is virtually impossible. The Maya were deliberately, carefully, and successfully building astronomy into their cities. The Dresden Codex and ancient books of the sky. Of all the astronomical achievements of the Maya that have survived into our time, perhaps none is more precious or more tragic than the Dresden Codex. This bark paper book, accordion folded and covered with glyphs and illustrations in red, black, and other colors, is one of only 4 pre-Columbian Maya books known to exist today. It is called the Dresden Codex because it somehow made its way to the Royal Library in Dresden, Germany by the 1700s, though how it left the Maya world remains a mystery wrapped in the violent confusion of the Spanish conquest. The Dresden Codex consists of 39 double-sided pages, though originally it was longer. It contains a wealth of information: astronomical tables, ritual almanacs, agricultural guidance, prophecies, and what may be the mathematical and observational work of specific Maya astronomers, whose names we will never know but whose genius shines through the centuries in these careful calculations. It was a German mathematician named Ernst Forstemann, working in the late 1800s with no background in Maya studies, who first recognized that the pages of the Dresden Codex contained sophisticated astronomical information. Examining a table of numbers on page 24, Forstemann deduced these were measurements related to Venus, despite not being able to read the hieroglyphic writing. This was a remarkable piece of scientific detective work, seeing the patterns in pure mathematics that pointed to the planet's cycles. Later, in the 1920s, a chemical engineer named John Teeple looked more carefully at these numbers and realized the Maya were using a sophisticated technique to correct for irregularities in the Venus cycle, much as later cultures would develop leap year systems to correct their calendars. This correction system in the Dresden Codex represents a genuine mathematical innovation, a discovery made by Maya astronomers at some point in their history and recorded for future generations. Recent work by scholars like Gerardo Aldana has taken our understanding even deeper. By combining the study of Maya hieroglyphic writing with archaeological evidence from Chichen Itza and astronomical calculations, Aldana makes the case that the Venus table in the Dresden Codex represents the work of a specific astronomer, possibly a woman based on iconographic evidence, working at Chichen Itza during a 25-year period in the first half of the 10th century. This astronomer, working in the observatory we now call El Caracol, made systematic observations of Venus over many cycles. They had access to earlier astronomical records, including observations made at Copan 200 years earlier. By comparing these historical records with their own observations, this individual realized how to create a correction factor for the Venus calendar, discovering a way to keep the predicted positions of Venus aligned with actual observations over long periods. This was not abstract numerology, but practical science, the solution to a real problem in astronomical prediction. The Venus table itself occupies pages 46 through 50 of the Dresden Codex. It's laid out as a grid showing Venus appearances on specific dates in the Tzolk'in calendar. The table covers 65 Venus cycles, or about 104 years, and includes correction factors that account for the drift between the ideal 584-day cycle and Venus's slightly shorter actual average period. A Maya priest consulting this table could determine when Venus would next appear as morning star, when it would vanish, when it would reappear as evening star. Information vital for timing rituals and perhaps military campaigns. But Venus wasn't the only celestial body tracked in the Dresden Codex. The document contains extensive lunar tables and eclipse prediction information. These eclipse tables include glyphs spaced at correct eclipse intervals, showing the Maya understood the roughly 6-month spacing between eclipse seasons and the longer Saros cycle of approximately 18 years. An almanac within the Codex can be dated to the year 924 based on the eclipse and calendar dates it contains, giving us a specific window into when this section was created. Other sections of the Codex deal with seasonal phenomena, agricultural timing, and ritual cycles. One almanac, covering 1,820 days, is structured as 20 rows of 91 days each, creating a 5-year table that aligns with both the solar year and various ritual cycles. Some captions associate equinoxes with Venus, helping scholars date when different sections were composed based on when this astronomical configuration would have been observable. The Dresden Codex is not the only surviving Maya astronomical record, just the most complete. The Madrid Codex, Paris Codex, and Grolier Codex all contain astronomical information, though in less detail. The Grolier Codex is specifically a Venus almanac, further evidence of this planet's central importance. These 4 books represent a tiny fraction of what once existed. The Maya were prolific writers, and many cities would have had libraries containing numerous codices covering history, astronomy, ritual, tribute records, and other subjects. When Spanish conquistadors and priests arrived in the Maya world in the 1500s, they systematically destroyed Maya books as part of their campaign to erase indigenous culture and religion. Bishop Diego de Landa, in a particularly infamous act in 1562, ordered the burning of dozens of Maya codices at Mani, describing them as containing nothing but lies of the devil. This cultural genocide destroyed an irreplaceable record of Maya thought and achievement, leaving us with just these 4 survivors. Yet not all Maya astronomical knowledge was lost. Carved in stone throughout the Maya world are hieroglyphic inscriptions recording dates, astronomical events, and historical occurrences. These stone books, immune to fire, have survived where paper could not. Stele, stone monuments erected to commemorate important dates, often include long counted dates along with supplementary series giving detailed lunar information. From these, modern scholars have been able to reconstruct significant portions of Maya astronomical practice. The inscriptions tell us that astronomy was being practiced across the Maya world. not just at a few major centers. Cities from the highlands of Guatemala to the northern Yucatan all participated in the same observational tradition, maintaining synchronized calendars and sharing astronomical knowledge. This widespread practice suggests astronomy was not esoteric knowledge held by a tiny elite, but a fundamental pillar of Maya intellectual culture, with astronomer priests trained at various centers and likely traveling between cities to share observations and refine calculations. What's perhaps most remarkable about the Dresden Codex and similar texts is that they represent the accumulation of knowledge across many generations. No single person could have compiled all the observations needed for its astronomical tables. These were community projects spanning centuries, with each generation of astronomers adding to the collective understanding, refining numbers, catching errors made by predecessors, and extending predictions further into the future. The Dresden Codex is, in a sense, a monument to patience, to the scientific method applied over vast stretches of time, to the Maya commitment to understanding the sky. Mathematics, the language of the heavens. Underlying all of Maya astronomical achievement was a mathematical system of remarkable sophistication. To track cycles spanning decades or centuries, to calculate corrections for calendar drift, to predict eclipses and planetary positions, the Maya needed more than observational patience. They needed mathematics capable of handling large numbers and complex calculations, and they developed precisely such a system. The Maya used a vigesimal, or base 20 counting, system rather than the base 10 system most of the modern world uses. In base 20, you count from 1 to 19, and then, instead of moving to a new tens place, you move to a 20s place. So, the number 21 would be represented as 1 20 plus 1, not 2 tens plus 1. This makes perfect sense if you're counting on both fingers and toes, giving you 20 digits total. The Maya represented numbers using a beautifully simple notation. A dot stood for 1, a bar for 5. So 2 dots meant 2, 3 dots meant 3. A bar and 2 dots meant 7. 2 bars and 3 dots meant 13, and so on up to 19, represented by 3 bars and 4 dots. Then came the innovation that truly set Maya mathematics apart from most other ancient number systems. They had a symbol for 0. The Maya 0 was typically shown as a shell glyph, though other forms existed. This Z0 functioned both as a number in its own right and as a placeholder, just like our modern 0. This might not seem revolutionary, but most ancient civilizations struggled with the concept of 0. The Romans had no 0, which is why Roman numeral arithmetic is so cumbersome. The ancient Greeks philosophically resisted the idea of nothing being something. The Maya, however, understood that 0 was a crucial mathematical concept, and they used it freely. In positional notation, the Maya wrote numbers vertically. The bottom position represented ones, or kin, single days. The next position up represented 20s, or wainal, in calendrical terms. The third position represented 400s, 20 times 20, and so on. To represent 0 units in any position, they would place the shell glyph there. This allowed them to write very large numbers compactly and perform calculations that would have been nearly impossible with most other ancient notation systems. There's one important modification to pure base 20 in Maya calendar mathematics. The third position was 18 times 20, or 360, rather than 400. This kept the ton, the basic year unit, close to the actual solar year of approximately 365 days. Above this level, the system returned it to pure vigesimal multiplication. This shows the practical flexibility of Maya mathematics, willing to adjust abstract mathematical elegance when reality required it. The long count calendar depended entirely on this mathematical system. Recording a date like 9/12/11/5/18, representing over 1.5 million days from the zero date, required facility with large numbers and positional notation, calculating when specific calendar combinations would recur, predicting Venus positions hundreds of years in the future, or working out eclipse cycles, all demanded mathematical skill. Maya astronomers performed calculations that modern scholars still find impressive. To calculate the average length of a Venus cycle accurate to within hundredths of a day required compiling observations over multiple cycles, perhaps dozens of them, and then computing the average with precision. To develop correction factors for calendar drift required understanding not just the immediate discrepancy, but how it would accumulate over decades or centuries. This was sophisticated mathematical reasoning applied to astronomical problems. The mathematical underpinnings also reveal something about Maya thought processes. They were comfortable with very large numbers, with thinking in terms of cycles that exceeded any human lifetime, with calculations that stretched deep into past and future. The long count could theoretically record dates billions of days in the past or future. While practically the Maya rarely used such extreme dates, the fact that their system could accommodate them shows a willingness to grapple with vast temporal scales. The precision evident in Maya mathematics also appears in their measurements. When building structures with astronomical alignments, achieving accuracy within a fraction of a degree required precise surveying and construction. While we don't have detailed descriptions of Maya surveying techniques, the results speak for themselves. Many Maya buildings are aligned to celestial events with a precision that would be respectable for modern construction, and the Maya achieved this with stone and wooden tools. This mathematical sophistication extended beyond astronomy. Maya cities required extensive engineering, from water management systems to massive pyramid construction. The planning and execution of such projects demanded practical mathematics for surveying, measuring volumes, calculating loads, and organizing labor. The same numerical facility that served astronomy served architecture, agriculture, and administration. It's worth noting that different Maya cities used slightly different variations of glyphs for writing numbers and calendar dates. Scholars have identified regional styles and changes over time, much as handwriting or font styles vary in modern writing. But the underlying mathematical and calendrical systems remained remarkably consistent across the Maya world, suggesting shared standards and regular communication between centers of learning. The combination of a sophisticated number system, the concept of zero, positional notation, and the practical application of mathematics to real-world problems placed Maya mathematics among the most advanced of any ancient civilization. When we marvel at their astronomical achievements, we should remember that those achievements rested on this mathematical foundation, on the ability to count, calculate, record, and predict with precision. Celestial gods and sacred time. For the Maya, astronomy was never purely a matter of numbers and predictions. Every astronomical phenomenon carried religious significance. Every planet was a deity. Every cycle a story of divine action. To understand Maya astronomy, we must understand that it existed within a worldview where the cosmos was alive, where celestial bodies were active agents in an ongoing cosmic drama that directly affected human affairs. The Maya conceived of time itself as divine. They called the various periods of time days, months, years, by names and glyphs that represented supernatural beings. These were not merely abstract units, but living forces, entities that influenced the character of the time they represented. Each day in the Tzolk'in calendar was ruled by specific gods, and the combined influence of the day name, the number, and other cyclical factors determined the day's overall nature, whether it was favorable for warfare, planting, marriage, or ritual. The sun was Kinich Aja, the sun-faced lord, a deity who daily died in the west, traveled through the dangerous underworld at night, and was reborn in the east each morning. Solar eclipses represented moments of cosmic crisis when the sun was imperiled, times requiring ritual intervention to ensure the sun's survival and eventual triumph. The sun's annual journey from northern extreme to southern extreme and back embodied themes of life, death, and regeneration. The moon was represented by various goddesses, often shown as young and old, reflecting the moon's phases from new to full and back again. The Maya recognized the moon as feminine, associated with fertility, water, and cyclical renewal. Lunar eclipses, when Earth's shadow fell on the moon, were significant events, sometimes depicted in Maya art as celestial conflict or transformation. Venus, as we've discussed, was among the most important and feared of celestial deities. Associated with warfare and sacrifice, Venus's appearances and disappearances were fraught with meaning. The period when Venus was invisible, passing between Earth and Sun, or behind the Sun from our perspective, was understood as the planet's descent into the underworld, a dangerous time when the boundaries between worlds grew thin. Venus's emergence, particularly as morning star after the 8-day invisibility period, was seen as a resurrection, the god reborn and potentially vengeful. The feathered serpent deity Kukulkan, equivalent to the Aztec Quetzalcoatl, became increasingly prominent in later Maya culture and was closely associated with Venus. The iconography of feathered serpents appears in contexts related to Venus observations, and the equinox serpent shadow at El Castillo connects architectural astronomy to this particular deity. Some scholars believe the transition of Venus from evening star to morning star, its disappearance and reappearance, was mythologically understood as the feathered serpent's own death and resurrection. The Milky Way held great importance in Maya cosmology, understood as a great sky river or road. Sometimes it was conceived as the world tree, the axis connecting underworld, earthly realm, and celestial heavens. The dark rift within the Milky Way, a region where interstellar dust blocks the light of distant stars, was seen as the Xibalba Bee, the road to the underworld. Certain Maya structures may have been aligned to the Milky Way's orientation, and ritual activities were sometimes coordinated with its position in the night sky. Constellations, though not the same ones recognized in European tradition, also populated the Maya celestial sphere. The Maya recognized patterns in the stars and gave them names and stories. Some of these remain uncertain, as the destruction of so many Maya books left gaps in our understanding of their stellar lore. But we know that certain bright stars and asterisms were tracked and held significance. The concept of the Lords of Time is central to understanding Maya temporal philosophy. In Maya thought, time was not an empty container into which events were poured, but an active force. Each period of time had its own character, its own supernatural being, who governed it and influenced what happened during that time. Historical events were understood to have occurred not just at certain times, but under the influence of certain temporal deities. The past could echo in the future because similar temporal configurations recurred, bringing similar divine influences to bear. This cyclical view of time meant that history could repeat in patterned ways. If a particular combination of calendar cycles had witnessed the founding of a city, the accession of a great king, or a military victory in the past, when those same cycles came around again, there was reason to expect similar portentous events. Maya royal inscriptions often emphasize cyclical connections, noting when kings performed rituals on calendar dates that matched earlier significant events, deliberately creating resonance across time. The end of calendar cycles was particularly significant. The completion of a Katun, approximately 19 and a half years, was marked with ceremonies and monuments. The end of a Baktun, around 394 years, was even more momentous. The famous 2012 date that received so much attention in modern pop culture marked the end of the 13th Baktun and the beginning of the 14th in the long count. For the Maya, this was indeed significant, but as a moment of renewal and transition rather than apocalypse, the beginning of a new great cycle rather than the end of all things. Ritual timing based on astronomical observations was a key function of the calendrical and astronomical system. Major ceremonies were scheduled to coincide with important celestial events or favorable calendar dates. The synchronization of earthly ritual with cosmic cycles was believed to maintain the proper relationship between human realm and divine cosmos, ensuring fertility, prosperity, and cosmic order. This was one of the primary responsibilities of ruling elites and priest astronomers. Maintaining this crucial linkage through proper ritual performed at proper times. The interweaving of mythology, religion, and astronomy meant that astronomical knowledge carried spiritual authority. To understand the sky was to understand the gods' intentions and movements. To predict celestial events was to demonstrate special access to divine knowledge. This may partly explain the tremendous effort the Maya invested in astronomical observations, the resources devoted to building observatories and training astronomer priests. This wasn't just intellectual curiosity, though that surely played a role, but a sacred duty, a way of participating in and maintaining cosmic order. Legacy and rediscovery. The arrival of Spanish conquistadors in the early 1500s marked the beginning of a catastrophic disruption of Maya civilization and astronomical knowledge. The Spanish conquest was not a single event, but a prolonged process of warfare, disease, forced conversion, and cultural destruction that unfolded over decades. Maya cities fell one by one, and with them fell the institutions that had maintained astronomical knowledge for over a millennium. Spanish priests, zealous in their mission to convert indigenous people to Christianity, viewed Maya religion as devil worship and Maya books as demonic texts. The burning of Maya codices, most infamously at Mani in 1562, destroyed the accumulated astronomical tables, eclipse predictions, Venus calculations, and mythological texts that formed the corpus of Maya written knowledge. Only the 4 codices that somehow escaped to Europe survived, and even these were not properly understood for centuries. The complex hieroglyphic writing system was deliberately suppressed. Children were forbidden to learn the traditional glyphs, and within a few generations, the ability to read and write in the ancient Maya script was lost. This amnesia extended to much astronomical knowledge, particularly the more technical aspects requiring written records and calculations spanning long periods. Yet Maya culture did not simply vanish. The Maya people survived. Their languages evolved but persisted, and fragments of their astronomical tradition continued in altered forms. Among some Maya communities, the Tzolk'in calendar was never abandoned. Daykeepers in highland Guatemala continued tracking the 260-day cycle through the colonial period, through an independence, through modernization, maintaining an unbroken practice that reaches back beyond recorded history. European scholars slowly began to recognize the sophistication of what had been lost. When the Dresden Codex was properly examined in the 19th century, mathematicians and early archaeologists realized they were looking at astronomical calculations of impressive precision. The decipherment of Maya hieroglyphic writing, a process that accelerated dramatically in the late 20th century, opened new windows into understanding. Texts carved in stone monuments, immune to fire, could finally be read, revealing historical records, astronomical observations, and the names and deeds of ancient Maya rulers and scholars. Modern archaeology has recovered immense amounts of information. Excavations at sites like Chichen Itza, Tikal, Copan, and hundreds of others have revealed the extent of Maya cities, the sophistication of their infrastructure, and the astronomical alignments built into their architecture. Technologies like LIDAR, which uses laser pulses to map terrain beneath jungle canopy, have revolutionized our understanding of Maya settlement patterns, revealing vast cities and ceremonial complexes previously hidden by vegetation. Researchers studying the astronomical alignments of Maya buildings have confirmed the precision of Maya observations. When archaeologists measure sight lines through El Caracol's remaining windows and calculate what those sight lines target on the horizon, they find exact matches with Venus's extreme positions. When they examine the orientation of pyramids and plazas, they discover solar and stellar alignments that could only be intentional. The architecture itself serves as a stone record of astronomical knowledge. Collaboration between archaeologists and Maya communities has enriched understanding of continuing traditions. Anthropologists working with modern daykeepers have documented how the Tzolk'in calendar is still used for divination, for timing agricultural activities, and for understanding personal destiny based on birth dates within the calendar cycle. This living tradition provides insights into how the calendar functioned in ancient times, interpretive keys that pure archaeological and astronomical analysis might miss. There have also been valuable corrections to earlier misunderstandings. For example, the infamous 2012 prophecy that captured popular imagination in the early 21st century was based on a fundamental misunderstanding of Maya thought. While the end of the 13th Baktun on December 21st, 2012, was indeed a significant calendar milestone, the notion that the Maya predicted apocalyptic end of the world was entirely a modern Western invention. The Maya long count continues beyond this date into future Baktuns, and there is no ancient Maya text predicting any kind of doomsday for that date. The legacy of Maya astronomy extends into modern science in unexpected ways. Scholars studying ancient astronomical observations, including those of the Maya, have been able to use them to constrain models of Earth's rotation, which has been gradually slowing over millennia. Ancient eclipse observations, including Maya records, provide data points showing when and where eclipses were visible, information that helps refine our understanding of long-term orbital dynamics. The accuracy of Maya astronomy without telescopes or modern instruments reminds us that careful observation, patient record-keeping, and intelligent analysis can achieve remarkable results even with limited tools. The Maya demonstrated that science is not dependent on technology, but on method, systematic observation, careful measurement, willingness to test predictions against reality, and transmission of knowledge across generations. Perhaps most importantly, the recovery of Maya astronomical knowledge has contributed to a broader understanding of human intellectual achievement. For too long, Western scholarship assumed that significant scientific and mathematical developments occurred only in certain favored regions: Greece, Rome, the Islamic world, later Europe. The depth and sophistication of Maya astronomy, alongside achievements of other cultures like ancient China, India, and the Islamic Golden Age, demonstrates that the scientific inquiry is a universal human capacity, emerging independently in diverse societies when conditions support it. Modern Maya communities increasingly take pride in their ancestors' achievements. Archaeological sites function as touchstones of cultural identity, places where contemporary Maya can connect with a past that was nearly erased. The fact that the Tzolk'in calendar continues in use provides a direct thread connecting the present to antiquity, a living inheritance that survived conquest and suppression. There are ongoing efforts to teach Maya hieroglyphic writing to new generations, to train young scholars in decipherment, and to involve Maya communities in archaeological research on their ancestral lands. This represents a kind of cultural healing, a reclamation of knowledge and identity. The astronomical and mathematical achievements of ancient Maya astronomers belong not just to academic history, but to the living Maya peoples as part of their heritage. As archaeological work continues, new discoveries emerge regularly. Sometimes it's a new inscription providing additional astronomical data. Sometimes it's recognition of an alignment or architectural feature that previous researchers missed. Sometimes it's a reinterpretation of known texts that reveals new layers of meaning. The story of Maya astronomy continues to unfold, each discovery adding detail to our picture of this remarkable civilization and its understanding of the cosmos. Closing, the eternal dance of sky and mind. As we approach the end of our journey through the astronomy of the ancient Maya, allow yourself to take a deep, slow breath. Let your mind drift back across the centuries we've traveled, across the calculations and observations, across the stone observatories and bark paper books, across the priest astronomers climbing pyramid steps in pre-dawn darkness to catch Venus's first gleaming appearance on the horizon. What we've explored tonight is not just a collection of facts about an ancient civilization. It is a story about human curiosity, about minds that looked up at the wheeling stars and refused to see only chaos or mystery. The Maya saw patterns, and they sought to understand those patterns not through divine revelation alone, but through patient watching, careful recording, and systematic analysis that we can only call scientific. They did this without telescopes to magnify distant worlds, without atomic clocks to measure seconds, without computers to crunch vast datasets. They used their eyes, their minds, and the tools available to them: stone and wood, bark paper, and natural pigments, the vigesimal number system they had developed, and the concept of zero they had discovered. With these, they calculated the length of the solar year to within minutes, tracked Venus's synodic period to within hours, predicted eclipses decades in advance, and created a calendar system that measured time across millennia. The Maya understood something profound about the relationship between observation and knowledge. They knew that a single observation tells you little, but hundreds of observations across decades begin to reveal patterns. Thousands of observations across centuries allow you to calculate averages and identify irregularities. Tens of thousands of observations, carefully recorded and transmitted from generation to generation, permit predictions of stunning accuracy. They were practitioners of what we might call big data astronomy, long before anyone imagined those words together. What makes Maya astronomy particularly beautiful is how it wove together multiple threads of human experience. It was rigorous mathematics and careful observation, yes, but also poetry and mythology. It was practical, timing planting and harvest seasons, but also spiritual, synchronizing ritual with cosmic cycles. It was an expression of political power, demonstrating elite access to divine knowledge, but also a communal enterprise spanning generations, with each astronomer building on the work of their predecessors. The observatories they built stand now as ruins, stones scattered and worn, windows collapsed, spiral staircases leading nowhere. But in their time, these were places of discovery, where individual minds grappled with the mysteries of celestial motion, and sometimes, like that astronomer at Chichen Itza in the 10th century, achieved genuine breakthroughs, solving problems that had puzzled earlier observers, finding the corrections needed to keep predictions aligned with ever-reliable reality. The Dresden Codex sits now in a climate-controlled case in Germany, its bark paper pages centuries old and fragile. But it once lay open on a table in a Maya city, consulted by priests determining auspicious dates for ceremonies, by rulers planning military campaigns to coincide with Venus's warlike appearances. It represented not just information, but power. The power to peer into the future, to anticipate the gods' movements, and align human action with cosmic inevitability. There is something moving about recognizing that the same sky the Maya studied is the sky we see today. Venus still traces its intricate dance between morning and evening appearances. The sun still marks the seasons with solstices and equinoxes. The moon still waxes and wanes through its phases. Eclipses still awe and frighten despite our understanding of their causes. The stars still wheel overhead in patterns that have barely changed in the few thousand years of recorded human history. When you look up at the night sky, perhaps you can imagine Maya astronomers looking at those same stars and planets, noting their positions, marking their movements, and adding their observations to the growing body of knowledge that would span centuries. There's a connection there across time and culture, the shared human impulse to observe, to understand, to find pattern in apparent chaos. The Maya remind us that science flourishes where patience meets curiosity, where society values and supports careful observation, where knowledge can accumulate across generations. They remind us that different cultures can develop sophisticated understanding along their own paths, that there is no single route to scientific insight. They challenge any notion that ancient peoples were somehow less capable of abstract thought or complex calculation than we are today. The same human minds that tackle quantum mechanics and chart the expansion of the universe were present in the Maya astronomer, carefully watching Venus set behind the jungle horizon, mind working through the calculations that would predict its next appearance. As you continue to rest, letting these thoughts drift through your mind like clouds across the night sky, perhaps you can appreciate the gift the Maya have left us. It's not just the specific astronomical knowledge they accumulated, though that is impressive enough. It's the demonstration that curiosity paired with careful method can unlock nature's secrets, that patience and record-keeping can reveal patterns that span lifetimes, and that the human mind, in any era, in any culture, is capable of understanding the cosmos. The story of Maya astronomy is ultimately hopeful. Despite the destruction of so much knowledge during the conquest, despite centuries of suppression, the tradition did not entirely die. The Tzolk'in calendar continues. The ruins endure, with their astronomical alignments still precisely pointing to solstice sunrises and Venus extremes. The 4 surviving codices preserve fragments of ancient understanding, and modern scholars, including many Maya descendants, continue to piece together what was lost, to read the stone inscriptions, to measure the building alignments, to recover and honor the intellectual achievements of their ancestors. If you've found peace and interest in this gentle exploration of Mayan astronomical wisdom, I hope you'll consider liking this video and subscribing to the Sleepy Science Society. These small actions help others discover this space where science and storytelling meet under the banner of calm and rest. You can share your thoughts and reflections in the comments, continuing the conversation that stretches back through those Maya priest astronomers still finding wonder in their cosmic observations. But for now, your work is done. You need carry nothing from this journey except perhaps a deeper appreciation for human achievement, for the patient accumulation of knowledge, for minds that looked at the sky and saw not just gods, but patterns that could be understood and predicted. Let your breathing slow even further. Let the tension drain from your shoulders, your jaw, your hands. Feel the weight of your body fully supported, held safely by the surface beneath you. The stars are still wheeling overhead, unseen perhaps, but still there, still following the same paths they've traced for thousands of years, paths that Maya astronomers mapped without the tools we take for granted today. Let your mind become as quiet and vast as the night sky itself. Let thoughts drift past like slow-moving planets against the stellar background, present but not demanding attention. You are safe, you are comfortable, and you are part of that long chain of curious minds stretching back through history, all looking up in wonder at the same eternal cosmos. The Maya understood that time is a cycle, always returning, always renewing. Let yourself rest now in this moment, this point in the great wheel of time, knowing that tomorrow the sun will rise again in the east, as it has for billions of days before, as it did when Maya astronomers first calculated the length of the solar year with startling precision. Rest well, peaceful traveler through time and stars. The cosmos continues its patient dance, and you are part of it, a conscious moment in the universe observing itself, just as those ancient astronomers were conscious moments in their time, all connected by curiosity, by wonder, by the simple human act of looking up and asking why. Good night.